Okay, welcome back to the lecture on design for quality. So, in the last class we spoke about how to quantify robustness. So, one of the metrics that we discussed was the SN ratio. SN stands for signal to noise. As I pointed out in the previous class, the idea of SN ratio emerges from electrical engineering, and the one who introduced it is Taguchi. Usually in electrical engineering you need to compare two different signals. The way signals are seen there is a mean signal and there is a noise around it. So, if you want to compare two identical signals, then you will look for the noise information in that, and it is usually dealt as a ratio. So, the signal becomes the mean value and then the noise is nothing but the standard deviation or the rate at which your signal is varying. So, if you want a signal that has minimal variation in that, it means the denominator in the SN ratio will be less. This translates to the SN ratio being more. So, if you are comparing two different signals and your criteria is to have less noise, then you are looking for a larger SN ratio. So, that is the same concept that we are trying to use here to quantify robustness. One simplest way of looking at robustness in a single phrase that you would like to say is minimize standard deviation. So, we are trying to use the ratio as signal to noise. So, that noise is nothing but your standard deviation, and the principle of standard deviation is to the principle of robustness is to minimize the standard deviation, which means for the same mean, if you are going to have a lesser standard deviation, then your SN ratio will be large. So, the idea of robustness would be to maximize my SN ratio. That is the whole idea of using SN ratio as a metric for robustness. So, as pointed out here, the maximizing SN ratio is equivalent to minimizing quality loss. So, the other day we also started to look at how this quality loss function is related to robustness. So, you remember the Sony TV example. Okay. So, this is my target. M is my target, and I would like to have my distribution as close as possible to this guy, okay, compared to a fatter distribution. Okay. So, imagine your loss function is like this. It is a quadratic function, right. So, what the loss function says is tries to stay as close as possible to your target value. The moment you deviate from your target value, the loss is correct. The y axis for the loss function is the loss. So, the moment you deviate from the target, the loss is going to increase, and the way in which it will increase is quadratic in nature. But there could be applications where the loss could be exponential, as we have discussed, nuclear power plant, gold and jewelry. Okay. It could be in an exponential sense, but what Taguchi said is most real life applications you can use a quadratic loss function. So, the other way of looking at it is, if you want to minimize your loss, you need to be as close as to your target. Do something in your design variables such that you stay close to your target. So is the story for robust design also. What robust design says? Minimize your variance. If you are talking about these two probability distribution function, the red and the blue, you would prefer the blue under the assumption that the mean for both of them is the same, because the blue has a lesser standard deviation than the red. So, you would prefer that. are you able to visualize the fact that the blue, which has a lower standard deviation, directly translates to a lesser cost, meaning quality loss, compared to the one with the red, okay? Because I am going to only utilize this region, maximum, like this region is what I am utilizing with respect to the blue curve, whereas I am really utilizing, if you see, like for instance this data, a data at this point is very far away from this target, which means there is a huge loss for me, okay. So, this is a direct overlapping of your quality loss function, and this is the concept of your robustness. Okay. This is where we are mapping quality and robustness. If you remember, okay, the other day I told you the first thing that we will talk about is quality. We will define quality verbally and we will see how to quantify quality. Okay. The second point that we told is we will also discuss about robustness, which we have done. We will define robustly what robustness, we will define verbally what robustness is, and we will see how to quantify robustness. How did we see verbally, how did we see robustness means?
Changing the output without varying the cause of the variation again.
Correct. Irrespective of your variations in the input, the output variation should be minimal or within the specified limits. That is what robustness is, that is a verbal description. How would you quantify that? Is using a standard deviation. So, if you are going to reduce the standard deviation of a given process, the process is supposed to be more robust. That is what is robustness, right. So, we have defined and we have also discussed on quantifying it. Now, we also need to bring about a relationship between quality and robustness. This is that relationship, because right now I have only discussed the concept of robustness and I have talked to you about the verbal description of quality, and then we also discussed on how to, or what is a metric that can be used for measuring quality. What is the metric? It is the quality loss function, and robustness, the metric is SN ratio. You see the idea, and you can see that these two are in principle related, because by assuring a robust design, I can say the product has a better quality. But there is one assumption that goes into it. What is that? It is not an assumption, it is a given condition also, which I stated. When I drew these two graphs and the quality loss function, I stated that.
Assume the mean to be same.
Very important observation. The mean has to be the same. Usually we say the mean of the process and the target. That is important, okay, because with respect to the quality loss function, there is a target. Irrespective of the target, your process has a mean. So, when you use the word target, it is usually for the quality loss function. I have a target, and how much did you deviate from the target on either side or on one side, depending on what type of problem you are discussing. A target and how much I am deviating from the target holds good for the quality loss function. So be your target, but I have a process and the process has a mean. Yes, you can bring the process mean to match my target, that is a different discussion, okay, but the terminology that is used, target for quality loss function, mean essentially refers to process mean, that will be for the robustness discussion in our context. Please understand, this is not in a global context. In the course of this particular offering, we are using these terminologies. Okay. When I use mean, it is usually the mean of the process, and when I use the word target, it is used for referring your quality loss functions target. So, sometimes there could also be a situation like this that brings us to this discussion. I have a target M, it is a straight line, I am not able to draw a straight line on this interface. Okay. I have a target M, and of course, I will define my loss function also based on that. The moment you deviate from that, should be a mirror. Okay. I did not mean to draw an asymmetric, but let us assume that it is an asymmetric loss function in this case. But I could have a process that runs like this. So, let us say for this green, sorry, this pink, let us call the word mu 1, let me call it. Okay. My target mu is the average of this rose or pink probability distribution function. This is the process variability. But I am looking at these loss for these conditions, and then I say this is not acceptable. So, what I do? I use some robust principles or the concepts for robust design, and I end up reducing the variation. So, in this case specifically the mean does not overlap on your target. It might still satisfy your quality conditions. The green is a robust design over your pink design, there is no doubt about it. But however, something that has happened here is there is a mean shift. I have done something in my process that the mean of the process itself has shifted. However, during the process the standard deviation has reduced. The standard deviation compared to the pink one, the green one is better, it is less in the sense. Okay. One thing however, you need to note is you always need to look for this, what is this? I do not know whether it is. You always need to look for this term, what is that? Coefficient of variation. So, it is basically sigma over mu. So, if you call sigma 1 for the rose and sigma 2 for the green, then you have to have sigma 1 over the mean and sigma 2 over its mean. In this particular case, we might not have that kind of a difference with respect to the mean, it is a small shift, but still it has shifted. Hence, one small update to our perspective on robustness. Robustness does not only involve reducing the standard deviation, but it also has to account for the mean shift. You cannot say I have a close to a straight line performance, but then my mean is away by about 10 meters. Every time you punch a hole, it will give you 10 mm. Yes, it is great, but however, my requirement is 7 mm. Your machine cannot adapt to 7 mm, there is no use. You do 100 million punches, every time it will give you 10 mm, sir. Good, no use for me, because my requirement is 7.5. So, unless you shift your process from 10 to 7.5, there is no use to me per se, and on top of it you can even have little leverage, you can make some errors. That is the advantage of this design paradigm. Rather than saying you have to design in such a way that the design will never fail. You understand? Do you understand the concept? This is a very nice paradigm. You accept to the fact that the failures will be there. You just try to make sure that the failures are less in number. Rather than saying you cannot fail, you are saying it is okay to fail, but let us figure out the ways in which we can minimize the failure. So, this is a more practical perspective. It is a new, it is a very interesting paradigm from a design perspective, okay, because there are a lot of parameter, attributes, factors that contributes to a particular design, and not all of that are under our control. This is where the concept of robustness kicks in. You might not be able to control all the factors. In spite of that, your product is expected to perform with minimal variation or within the specified bounds. Hence, you need a framework to carry out such a design, and that is what is a robustness design. Okay. So, this is the whole idea, this robustness and the QLF loss function. So, the QLF is a metric used to measure quality, and robustness is a concept, and just now we see how you can use robustness as a tool to achieve quality. So, that is the relationship that we wanted to establish. If you recall, the title of the book, the Fatke's reference book for this particular segment, is that it involves both quality and robustness. So, the concepts from robustness are used to drive quality. So, there is necessarily a difference between quality and robustness, and the other day we also discussed what reliability is. So, as we have discussed so far, quality is predominantly used and refers to a product at the manufacturing phase. The moment manufacturing is over and as a manufacturer I sell it to the user, the performance of that with respect, the performance of the product with respect to the user is called the reliability. How well the product lived up to its expectations or the promise that the manufacturer made is called reliability. That again is nothing but a ratio. It says I sold 1000 products and about 998 products were fine. So, what is your probability of failure? 2 over 1000, that is what is my probability of failure. So, your probability of success is just 1 minus that ratio or 998 divided by 1000, that is all. 998 products worked fine, but you cannot apply this concept for everything that you design. For instance, aircraft, how reliability is taken care of in an aircraft is by introducing redundancy. All aircrafts can fly with one engine. Why do they have 2 engines? Because if the one fails, gone. So, the second can kick in, they can actually manage to fly. There will be some unbalance issues because the other one is not rotating, but still they can land. So, the redundancy is used as a way to ensure reliability. In a similar fashion for medical devices, there are certain medical devices that you cannot afford to talk about reliability numbers. They have to work every time, whatever may it be. So, they use redundancy. In our computer center, there are 3 levels of backup. There are backup for a UPS because certain data cannot be lost. So, they have to be preserved, and whatever may the case be, they will be preserved. So, this is one way of ensuring robustness and reliability, but the other classical way of looking at reliability is to do what? Redundancy. This is as good as saying I will carry two phones. If one fails, I will use the other one. If one charge is over, I will use the other charge. Correct? That is what usually these travel executives do. If you see, their bags are really heavy sometimes, but their laptops are very small, very thin. Then you look into their bag, they will actually carry a additional battery, because they have a long flight and they might not be able to charge their laptops on the flight. So, they will carry a charged battery with them. Once this battery drains down, they will put the other battery and then they will start working. So, that is a redundancy mechanism. Okay. So, an intermittent summary on the 3 bullets that we saw as learning outcomes of this particular segment. The first one was about the definition of quality, how to measure quality. The second one was about robustness, how to quantify robustness. The first bullet here kind of combines those two. How to reduce the performance variation during functioning. When I say function, it is functioning. That is something that we need to talk about, how to reduce, but how it can be measured is something that we have discussed. And it should also account for all types of cost, whether it is operational cost, manufacturing cost, R&D cost. The third one is the tools. For instance, signal to noise ratio is a metric, it is allowed to use, it is allowed to measure robustness, and you can use quality loss function to measure quality. In a similar fashion, we need to now learn about design of experiment that will lead to parametric design. Before going into design of experiments, we will step back a little bit and try to look at this entire discussion as a design for Six Sigma. If you look at it, how the design over the years has evolved. If I am not wrong, we have discussed this already. First, getting the performance was important. Get it to work, that is what we say in our product design lab first. Get it to work, because form follows function. You need to first show me that it will function. If you are designing a car, you show me it goes from A to B. Then let us worry about what is the color of the car. First, you need to tell me whether the device can take you from point A to B. So, the function. Then comes the form. Form follows function. This is a pen. What is the function of the pen? It should write. Who will write? Human beings will write. How will they write? Using their hands and fingers. Okay. How are they going to use their fingers? They need to hold it. They will use predominantly these 3 fingers, or some people might use their 4 fingers. Okay. Okay. If that is the case, how am I going to hold it? I am going to hold it like this. So, a pen has to have certain dimensions and shape, so that the holding becomes easier for me, it becomes intuitive for me. That is the form. Can I design a pen like this? Yes, I can always design a pen like this. I can design a pen like this. But the problem is I am going to use the same 3 fingers, but it is not as comfortable as, or can I design a pen like this, like a ball? You can design, yeah, why not? You can design a pen like this, where you use all your 5 fingers to hold it and then be able to write it. But we all know the most easiest and the intuitive way to do that would be this. Hence, first you need to, if you are designing a pen, you need to make sure that it is writing. Then you need to worry about, oh, should it be a triangular cross section, should it be a rectangular cross section, or it should be a cylindrical cross section, how big should it be, because form follows function. So, in the design theory, the evolution of the design itself, people were first ensured function, then comes form. So, if you look at it, lot of decades ago, people were worried only about the performance. It has to do that. But once the device itself has been in the market for a while, you need to ensure that it does the function every time you want it to do the function. You cannot say, okay, I sell about 100 and 80 times it will work. That is a very bad ratio. At least in paper, 100 of them should work. 100 of them will work to begin with, but that is why they give you the warranty period. I know that there could be errors, but what I can guarantee you is for 5 years my powertrain will run without any problem. That is the confidence that I have in almost all my engines. In almost all my engines, only 5 years. There is a chance that 1 out of 1000 engines might fail after 5 years. 1 out of 1000 is a very good number for man-made products. So, first it is about ensuring function, then the second is ensuring it functions every time that you want it to function. That is sometimes called reliability, durability, and the concepts of quality and robustness also come at the same time. Okay. They can be discussed in the same frame. Now, that is where the design for Six Sigma comes into picture. So, what the concept says is, today if you are designing a product, not a single company, I mean most of the products, not a single company does all the components. You go to a subcontractor, you have a vendor who will supply some parts to you, but you cannot ensure a Six Sigma product without ensuring a Six Sigma component. There can be variation in the component performance, but it cannot fail often. If it fails, let us say that there is a component supplier who supplies 100 components, out of which 50 will fail, and these components go into a larger product which a company manufactures. If that component fails, the product will fail. 50% of the times the product will fail. You cannot afford to do that. So, if the product needs to be at the Six Sigma level, almost all the components that feed into it should also be Six Sigma, at least theoretically. There are some criticality issues. Not every nut and bolt needs to follow a Six Sigma stuff. There are failure levels, low risk, high risk, medium risk. Obviously, for high risk you need to be in a Six Sigma. Let us say that you are supplying a part to the brake, you are supplying a part to the airbag. You have to be maybe not even Six Sigma, some higher Sigma guy. It cannot you cannot afford to fail. Whereas you are just supplying an audio system, you can afford to fail. It is not going to be a very critical failure even if it fails. The user experience guy will come and blast you, but from a criticality, from an occupant safety perspective, that is not that very critical. You can go for a less Sigma manufacturer if you want. So, depending on the criticality, the Sigma will be, can be increased or decreased. So, I just wanted to tell you, in a design sense, people first did design for performance, then design for reliability. Currently we are talking about design for sustainability. Right now the idea is only, it is called the reactive design. We have used our electronic products, for instance our printer cartridge, that is the one that is used widely in the discussion. We have bought it, we have put it inside the printer, we have printed thousands of pages, then one day it shows the printer cartridge is over, you need to replace it. We have bought the next printer cartridge also, we have removed the old printer cartridge and we do not know where to throw it, because we have read somewhere that this is an electronic stuff that you should not dispose just like that, and there is no system that says come and deposit all your printer cartridges here. So, this is called reactive design. After usage we worry what to do. So is the case with our water. We have depleted all the water resources and now we are saying, oh I am not sure, how do we manage water now? Instead, at least for the sustainability perspective, what people are now started advocating is, you need to enforce an active design, not a reactive design. Do not respond after the function is over, after the performance is done. At the concept level, you should ask these questions on if you are going to use this material, after its usage what are you going to do with that? How are you going to dispose it safely? You need to bring that. Yes, if you use an alternate material, it might influence a cost, it might burn a hole in your wallet, that is fine, but you need to make that decision at an early concept stage. So, it is called design for sustainability now. People are now coming up with metrics for sustainability and including it at the design stage. You need to choose material or you need to choose design methods that are sustainable in nature. So, like that, from a manufacturing perspective, people spoke about design for Six Sigma. You cannot say I will buy my components from wherever I want, but then my product has to be Six Sigma. You cannot say that. You will have to ensure as many as possible all the components that come also follow a Six Sigma process, then it is relatively easier for you to ensure a Six Sigma. So, Six Sigma, if Six Sigma is required for the product, then it also has to be ensured at the input level. That is what Six Sigma, design for Six Sigma means.